Hello, I'm Igor Oliveira, and in this talk, I'm going to tell you about a connection between quantum learning algorithms and circuit lower bounds. This is based on joint work with Srinivasan Arunachalam, Alex Grilo, Tom Gur, and Aarthi Sundaram. Our main result established a new connection between two fields, algorithm design, where we would like to find faster algorithms, and complexity theory, where we are mostly interested in impossibility results known as complexity lower bounds. These are theorems showing that some problems of interest cannot be solved with limited resources, such as time. And surprisingly, connections between these two areas have led to major advances in these fields in the last decade. Two notable examples that we have are the ACC zero circuit lower bound established by Williams using the design of a SAT algorithm. And in the other direction, CIKK, who used techniques from complexity theory in an almost generic way to obtain a new learning algorithm for a class known as AC0 parity. So in this work, to the best of my knowledge, we established the first general connection between the design of quantum algorithms and complexity lower bounds. Before explaining this connection, let's briefly look at the state of the art in both circuit complexity theory and learning theory. One of the most investigated modules in complexity theory is the Boolean circuit. Here we are interested in computing a Boolean function mapping n bits to a single bit. And we represent computation as a sequence of elementary operations known as the gates of the circuit. So in this particular example, you see a circuit that has access to the n input bits represented by the variables, and it computes according to a collection of gates. We have 6 gates in this example, so the size of the circuit is 6. And also the depth of the circuit is 3, which is the longest path from an input variable to the output gate. The reason, or one of the reasons we are so interested in Boolean circuits is because they are able to represent any computation. And in particular, if you have a polynomial time algorithm, then there's a way to construct from it a sequence of polynomial size circuits for the same problem. And as a consequence of this simulation, if we can show that there are problems in NP that do not have circuits of polynomial size, then we get a proof that P is different from NP. Obviously, a lot of work has been done in trying to understand the power and limits of different classes of Boolean circuits. And today we have a reasonably good understanding of circuits where the depth is restricted to be a constant, say 20 layers, that's independent of n, the length of the input. But even in the case of constant depth circuits, if we increase the set of allowed gate types, for instance, if we allow a gate that can take the input bits and compute the sum modulo 6, then it's already tricky to understand the limits of such circuits. Still, most researchers, they believe that there are problems in NP that can be solved by circuits of polynomial size, and that this is a promising way of attacking the P versus NP question. But at the same time, it is consistent with our current knowledge that even problems that we can solve with exponential resources, like non-deterministic exponential time or even quantum exponential time, it's still possible that all these problems, they admit Boolean circuits containing only polynomially many gates. So it is still possible that quantum computations of exponential size can be classically simulated with only polynomially many gates. For the purpose of this talk, I would like to use as a running example the class of threshold circuits. So these are also constant depth circuits, but here we expand the gate types and we allow the circuit to compute a threshold gate. So this is just a Boolean function that can be computed in the following way. We take a weighted sum of the input bits, of the input wires in the circuit, and we compare this weighted sum with a fixed threshold t, and the output is 1 if and only if the sum is at least t. So it's not hard to see that a single such gate is quite weak. It can't even compute the parity function. But once we compose just 2 layers of threshold gates, they become much more interesting. Such circuits can describe objects like a polytope with polynomially many facets. And as far as we know, any algorithm that runs in exponential time can be simulated by threshold circuits with just 2 layers and polynomially many threshold gates, which is quite surprising. We don't expect that just 2 layers of threshold gates can solve problems that admit exponential time algorithms, but this is still open. Our main result establishes a connection between proving circuit size lower bounds and designing new learning algorithms. Let me start by introducing the learning model of learning with membership queries under the uniform distribution. So here there's a fixed class C of Boolean functions. You can think of C, for instance, as the set of functions that admit small depth 2 threshold circuits. Now the learning algorithm is given query access to some unknown function from the class, meaning that it can query the function at any point. And after it interacts with this function for a while, its goal is to produce a hypothesis H that provides a good approximation to the unknown function. By that, we mean that the probability of a uniformly random point, h of x is different than f of x, is at most epsilon. Epsilon is called the error parameter of the learning algorithm. And we can consider different extensions of this model. For instance, if the learning algorithm is randomized, then we require that with high probability, hypothesis with error at most epsilon is produced. For our results, the stronger the model, the better. This is because we show how to get circuit lower bounds from the design of learning algorithms. So if you can design your learning algorithm in a stronger model for which this task is easier, this is a stronger connection. Learning algorithms for several expressive classes of functions have been discovered. For instance, there's a polynomial time membership query algorithm for the important class of DNFs. We also have quasi-polynomial time learning algorithms for different classes of constant depth circuits. But here, similarly to what happens in circuit complexity, as we increase the allowed gate types in the circuit, then many questions remain wide open. For instance, if we allow threshold gates in the circuit, then a single unknown threshold gate can be learned in quasi-polynomial time. But once we consider 2 layers of threshold gates, the depth 2 threshold circuits of polynomial size, then even if you would like to learn them in time slightly less than 2 to the m, there is no known algorithm for this task. So the class of depth 2 threshold circuits is a nice example of a class for which we currently have no interesting lower bounds, and at the same time there's no learning algorithm. So even if you would like to learn just 2 layers of threshold gates, so this can be seen as a very shallow discrete analog of a neural network, we have no algorithm that does better than 2 in time. And it naturally motivates the following question: can we use quantum computing to get better learning algorithms? So to formalize this question, we consider the standard extension of the learning model, where now the learner is quantum and it has quantum query access to the unknown function, so it can make queries in superposition. This is the standard model, so on an input x and b, the query returns x and b parity f of x. And in addition to making these queries in superposition, of course, the learner is able to perform quantum computations over the data. So this is modeled as a sequence of unitaries where we also have access to a black box, which is the unitary that computes f, the unknown function. And the goal is similar. With high probability, now over the output measure of the quantum circuit, we would like to produce a good hypothesis H, which has error at most epsilon. Quantum learners, they are potentially much more powerful than deterministic and randomized learners. For instance, even if we don't think about the query access, if we only look at quantum computations, then we have much faster algorithms for central problems. And the main question here is, can we use quantum computing to achieve quantum learning speedups? And concretely, can we learn 2 layers of threshold gates in quantum time that is slightly less than 2 to the n? So unfortunately, this is still open. As a quick summary, we have discussed both learning theory and complexity theory. In learning, we have some form of access to an unknown function, and we would like to approximate the function after making queries. In the case of quantum learning algorithms, we can make quantum queries. And in complexity theory, we are trying to show limits of a class of circuits, and the goal is to provide concrete examples of problems that can be solved by circuits in the class. And I have emphasized the role of depth-2 threshold circuits as a natural class of Boolean circuits for which we have no learning algorithms and at the same time no non-trivial complexity lower bounds. In this work, we create a bridge between quantum learning algorithms and circuit size lower bounds. Fix any circuit class C of polynomial size circuits. We show that if there's a quantum learning algorithm for C that runs in time slightly less than 2 to the n and learns functions in C with error slightly less than 1/2, then there's a problem that you can solve uniformly in quantum exponential time, but that does not have circuits from C of polynomial size. So this is a connection between quantum algorithm design and circuit lower bounds. Previously, a connection between classical learning algorithms and lower bounds was known, but extended to the quantum setting turns out to create significant challenges. As a concrete example of the connection, let's fix C to be the class of depth-2 threshold circuits of polynomial size. And let's fix the error parameter epsilon to be 1/4, so the advantage gamma is also 1/4. Then, immediately from the new connection, it follows that if this class of circuits can be learned with this error in quantum time that is just slightly less than 2 to the n, then we get a problem in BQE that is not contained in this class. In other words, what seems to be a rather minor algorithmic progress will lead to a striking consequence in complexity theory. Let me also highlight the tightness of the connection with respect to the involved parameters. For this, we consider 2 trivial learning algorithms. They are trivial in the sense that they work for any class of functions. So the first one is the algorithm that just queries the unknown function on all points. It runs in 2 to the n time. And our result is saying that if you can do anything better than 2 to the n time, then you get lower bounds. So the connection is tight with respect to running time. The connection is also tight with respect to the dependence on the advantage parameter gamma. Because using the power of quantum computing, one can show using Fourier sampling that any unknown function can be quantumly learned in polynomial time with advantage that it's slightly better than trivial. And by inspecting these parameters, we notice that the gamma square dependence is necessary in the connection. So finding an algorithm that runs in polytime and achieves slightly better advantage would also give us non-trivial lower bounds. For this reason, because we only need to beat these 2 trivial algorithms, we say that our result is really stating that the design of non-trivial quantum learners is sufficient for circular lower bounds. There are 2 ways to interpret this new connection. The first one is the optimistic interpretation, and it views our result as saying that it is a new path to lower bounds that explores the power of quantum computing. So if you can design a quantum learning algorithm, you can understand the limits of a circuit class. But there's also a pessimistic perspective, which is that given that proving circular lower bounds is so challenging, it has resisted so many efforts, one can view our connection as saying, maybe this is why it is so hard to use the power of quantum computing in the learning setting. So designing learning algorithms even with quantum computing is hard because it will lead to breakthrough lower bounds in complexity theory. Over the last few minutes of the talk, I would like to tell you about the techniques we use to extract hard computational problems from quantum learning algorithms. As we increase the power of the learning model, extracting computational hardness becomes a more delicate task. To achieve this in the quantum setting, we introduce a new modular approach that relies on pseudorandom generators. This is conceptually simpler compared to previous approaches, but the PRG construction requires significant technical work. Over the last few minutes, let me briefly go through the main stages of the proof. Fix a circuit class C, and suppose that we have a non-trivial quantum learning algorithm for C. The first step of the proof is to obtain what is called the quantum natural property against C using the learning algorithm. A quantum natural property is just a quantum algorithm that is given as input an entire truth table representing some Boolean function f, and is able to distinguish between two cases. The first is when the function is in C, where we would like to reject with high probability. And the second case is when the function is in a sense far from C and looks like a typical random function. In this case, we would like to accept the input function with high probability. The way we are able to distinguish between these two cases is by simulating the quantum learning algorithm using the input truth table. It is possible to show that when the function comes from C, the learner succeeds, while for a typical random function, we cannot expect the learning algorithm to succeed with high probability. Using the quantum natural property, we have an efficient quantum algorithm that is able to accept a dense set of functions that does not overlap with C. What we would like to do now is to find some function in this dense set, since this function is not in C. The way we achieve this is by using a pseudorandom generator. Pseudorandom generators are particularly helpful when we'd like to fool an efficient test. In this case, our test is the quantum natural property. We're going to use the PRG to generate a string, which is a truth table that is accepted by the test, and therefore it's not contained in C. The main issue is, how do we find this PRG? Can we get a PRG that is strong enough to fool quantum computations? We address this issue by using a non-constructive win-win argument. In the first case, we build the necessary PRG under a hardness assumption. In the second case, if we assume that the hardness does not hold, then quantum computations become so powerful that we are able to find a hard function directly by diagonalization. In both cases, we are able to get a language in BQE that does not admit small circuits from C. This sketch omits subtle issues. Please check the paper for details. To complete the proof, we must design the pseudorandom generator that fools quantum computations. This is our main technical contribution. Under the assumption that polynomial space doesn't admit sub-exponential time quantum algorithms, we show that there is a PRG with exponential stretch that is able to fool quantum computations. The analysis of the PRG is technically complex. Typically, when analyzing randomized classical algorithms, we can often reduce the analysis to the deterministic case. But in our setting, quantumness is inherent and can be eliminated. In particular, we provide an extension of a local list decoding algorithm of IJKW to the setting of quantum circuits, and this extension requires a delicate analysis. Let me finish the talk with some directions and open problems. The first one, of course, is design non-trivial quantum learning algorithms. And in particular, can we get a non-trivial algorithm that learns the class of depth-to threshold circuits? Using our connection, you could either design a slightly faster algorithm or a polynomial time algorithm that achieves a non-trivial correlation. And secondly, what is the power of quantum natural properties? And is there one against the class of ACC0 circuits? This would also lead to new lower bounds, and there might be some ways of approaching this question. If you're interested in learning more about this work, Go and check Alex Grillo Simon's talk, which provides more technical details. Thank you.